Depressions of any kind would change through time and be of various shapes and sizes. By analyzing the pattern of the isobars, it is possible to identify the shape of the low pressures. If we can see the isobars forming a finger-like protrusion away from the center of the low, then we call this an isobaric trough of low pressure. Trough weather can be as active and occasionally even more active than that of a main depression. Looking at the diagram, the surface winds tend to converge along the trough line. This results in a convergence zone that encourages the air to rise. This convergence zone can be very active, and areas of convergence need to be monitored very closely for potential weather. The weather around these troughs is very similar to that of the main depression itself. With all the potential problems of cloud, precipitation, icing and turbulence. There is another type of surface trough that is caused by upper air processes. These are known as trough lines and are represented on charts with a solid black line. These troughs are significant and have weather that is very similar to the cold front with active cumulo-formed clouds. This brings to a close one type of pressure system, namely the low pressures. But if you remember, the other major pressure system we need to look at is high pressures or anticyclones. To generate a high pressure at the surface, the weight of a column of air must be increased. In other words, there must be a net gain of air to the column. As the surface pressure increases, air will move outwards and away from the high. This will cause a general descent of air towards the surface. This is sometimes referred to as subsidence or sinking air. We can now summarize that air within a high pressure descends and diverges. This movement can be achieved in two main ways. These different ways define what type of high pressure it is. The first types are called permanent warm anticyclones. The reason for the name is because they tend to create very warm, dry surface conditions. Let's look at the reason why. If you remember back to low pressures, we stated that if air was forced to rise, it would cool adiabatically. In this type of high pressure, the reverse is the case. In the upper atmosphere, we can have an excess of air. Therefore, air will be forced to descend towards the ground. As this happens, the air is compressed under the increasing amount of pressure. And this causes the temperature to rise. We call this adiabatic warming. When the air eventually reaches the surface, it can be relatively warm. But remember, the reason for the high pressure was because of a net gain of air in the upper atmosphere. If we look at a global picture of the Earth and then briefly examine the major air circulation patterns, we can find areas where we have an excess of air in the upper atmosphere. In the areas highlighted, you can see air is converging in the upper atmosphere, creating a net gain of air. The air then descends and warms. We find these warm anticyclones between the Hadley cell circulation of air and the ferrule circulation of air. These high pressures form two bands around the Earth. From about 20 degrees latitude to about 45 degrees latitude, they form what is known as the subtropical oceanic high pressure belt. This belt will move north and south with movement of the sun moving to higher latitudes in summer and lower latitudes in winter. The subtropical highs tend to give very stable fine weather. The reason is relatively simple. In order to create cloud, condensation must take place, therefore air must be cooled to dew point. However, in these high pressure systems, air is sinking and warming, and therefore condensation is prevented. This means that any significant cloud development is very unlikely. This has an additional effect. Outside the summer months, when we have long nights, the Earth cools quite substantially, especially when there is no cloud. Even though the air could be quite dry, the temperature may fall enough during the night so that the dew point is reached. This would cause condensation and cloud to defell upon the surface next to the cold land. We call this radiation fog. It can be quite a common feature with high pressures, especially in winter and spring, and is more often seen in the morning. The small islands found in the oceans underneath the subtropical highs demonstrate the warm fine weather that we would normally expect within the warm anticyclones. The weather in these areas is hot, very dry, and of course clear of any cloud. Classic areas are the Azores and Bermuda highs in the North Atlantic. Over the land though, because of the extremes of temperature and lack of moisture, we find our major deserts. There is another way to generate a high pressure and for air to descend. If the land surface is very cold, then this will call the layer of air in contact with it. This will in turn call the layer of air immediately above, and so forth. These layers of air will slowly get heavier and sink as this cooling continues. The result is a gentle widespread subsidence of air, creating a cold anticyclone. These anticyclones are very common over large land masses in winter, where the ground cools very rapidly compared to the sea. These are apparent especially in Siberia and North America during the winter months. These areas can have extremely low temperatures with clear, very frosty skies. The cold anticyclones are also found over the poles, creating the polar highs. They tend to be weaker though, and other systems can pass through and disturb their development. The final type of anticyclone is one that is more transient, smaller in size, and of short duration. As such, it is termed a cold temporary anticyclone. In fact, this anticyclone is really a ridge of higher pressure, found between two polar front depressions. It is temporary to a person under its influence, since the ridge will move with the polar front as it travels from west to east. If we just discovered that within the high pressure there will be little or no cloud, then surely we would expect little or no precipitation. It goes to say that if there is very little chance of any water droplets, let alone any supercooled ones, then the risk of any icing is fairly slight. Because the descent of air is relatively widespread, it is unlikely that any significant vertical movement of air will develop to disturb aircraft. We can therefore say the risk of any low-level turbulence is minor. Next, we shall look at the visibility we might find within high-pressure systems. In warm anticyclones in particular, we have large-scale descending warm air. However, there is a layer very close to the Earth, which is unaffected by this warm descent. As a result, this layer of air will be cooler than the warm air above. This creates a temperature inversion. These are known as subsidence inversions and mark the point where temperature abruptly rises with height instead of falling with height, which is normally the case. This causes the layer to be very stable, and as you will see in the next scene, this has a significant impact on the visibility. If we know that large amounts of air are being drawn down towards the surface, surely then any particles from industry and agriculture will be held against the surface. The visibility over land would therefore deteriorate whilst the high pressure was dominating the region. Sometimes, whilst on the climb out from an airfield, you can notice the top of this poor visibility layer. This is a very good indication of the subsidence inversion. The movement of air within an anticyclone is also of huge importance to aviation. We already mentioned that air is descending at the center of an anticyclone and then diverges outwards along the surface. However, the high pressures are of such a large scale that the wind along the surface is deflected by the Coriolis force. If you remember, it deflected winds to the right in the northern hemisphere and to the left in the southern hemisphere. In summary, we can say that air moves around high pressures, clockwise in the northern hemisphere and anticlockwise in the southern hemisphere. Notice here that the isobars are widely spaced, indicating light winds. By analyzing the pattern of the isobars, it is possible to see the shape of the high pressure. If we can see the isobars forming a finger-like protrusion away from the center of the high, then we call this a ridge of high pressure. Ridge weather is usually identical to the weather found within the main high pressure. Air is still descending and diverging. Having seen the two main pressure systems and their weather in detail, we need to analyze the last of the pressure systems, coals. A kernel is quite special in that it represents an area not directly under the influence of either a high or a low pressure system. In fact, it is the region in the middle of two lows and two highs. Note that within this region, the isobars are very widely spaced. Because of the wide spacing of the isobars, the wind found within a kernel is very light and variable. Other than the wind, the weather within a kernel is dependent somewhat on the season. Generally, over land areas, we can say that in summer typical kernel weather would be thundery. Whilst in winter, it is mainly very foggy.